dual space. That is really taking dual space.
Dual space is because the outer evolution. Let's see duality. I mean,
the Quiver has a symmetry.
I mean, I did a study with Jimmy. There's a lot of way through higher order.
所以你不要局，也不用局限在一个。现在我给你们我也是。
Yeah. Okay.
Yeah.
Thank you.
That's not in your favor. It was exactly the title of your paper. What I classical groups. Of course, there are other groups. Population.
Professor Philsang Yoo from National University, Library, Calabi-Yau, and Tensor-Product BPS paper.
Okay, thanks a lot. Thank you for the invitation. I was actually pleasantly surprised to get an invitation here because I don't really think about Higgs bundles. But apparently, I was told that I was invited for physics, not even for physics or Higgs bundles. Physics, I mean, try to say something about that. So the first slide is just my own justification for myself, like why I am like any right to be invited. So I just want to say like how my talk may be related to Higgs bundles at all. And for that, you know, the Higgs bundles enter this like physics quantum field theory in at least like two different ways. And one is geometry elements, which I think you're going to hear a little more from BPS in the afternoon. And also like there are more big property teaching systems, which we heard a lot. And that has to do with what's class set theory. This slide is not necessary to be understood, but the point I want to make is that these Higgs bundles on the Riemann surface with some marked points that can be understood as a Coulomb branch moduli in sort of special complex structure. I actually want to get there, but at the moment I'm kind of very far from there. The expectation is that the 4D theory people talk about, basically kind of what I do. Part of what I do is that a lot of mathematicians took some parts of what physicists kind of say as a starting point, but I don't quite like that. I want to sort of take the starting point to be sort of the way before. So I want to kind of define the 4D theory in terms of some Calabi-Yau category, which I'm going to explain a little more later. And then starting from there, I want to really understand like what physicists do purely from this kind of categorical homological perspective. And that involves like something like homological algebra, like a vertex algebra, or this sort of thing. But the best I can imagine to get is some generic complex structure. I don't really know how to get the complex structure that sees Higgs bundles as of yet. Anyway, that's at least I want to get there. That's kind of as far as I can relate myself to these comments. And like very modest goal today is I just want to understand this kind of C3 Calabi category to understand this 4D theory. That's where I am. So I just started thinking about this topic very recently, so I didn't get very far. So somehow like preparing for this talk made me organize my thoughts. So thank you for that. Okay. So next thing I want to say is that my talk is going to be organized in a sort of Rashomon way, if you know what that is. So this is the name of a movie of Kurosawa. It's kind of an interesting movie. So if you don't get anything out of the talk, you at least got a movie recommendation. Very good movie. The point of this movie is that somehow there is something happened, and then the story is told by like 4 different people. It's just kind of all different. So it's kind of you're kind of putting pieces together to see what's happening, and it's kind of interesting. I think that's the format that I want to take today for various reasons. First of all, I mean, I'm in Japan, so I just want to homage to crosstalk movie. Another is, we have this very diverse background, and I just figured that even if I focus on one topic and just try to make it accessible, because of the difference of backgrounds, it's not quite going to be like working for the entire 45 minutes. So I just want to give some ideas for each part. So each part actually can be made into a sort of talk on its own. It's like really kind of independent talk. But I just wanted to have all these 3 different perspectives kind of combined into a single talk. So it's going to be like a rather brief some parts. But so I don't really expect like anyone to understand everything, but hopefully like everyone can get something out of it. That's the goal of the talk. And yeah, I'm going to talk about physics talk, algebra talk, and geometry talk. Okay, let me start. So each talk kind of consists of like 5 slides. So I don't have like that many slides. So you can just feel free to ask questions. Okay. So let me start with physics. So Chakotina Slivaka in 2010 introduced and studied some 4D theory, starting from string theory. So because I kind of most of the audience members are kind of mathematicians, for the physics part, I will try to say in terms of sort of the input-output data. Meaning, so what they say is if you choose like a pair of AD types, G and G prime, then you construct some Calabi-Yau sweeper, and using that, string theory is supposed to be 10-dimensional, and you have this Calabi-Yau sweeper, which is 6-manifold, and you do something, and you end up with 4-manifold. That's what I mean by this 4D equal 2 theory. So input is GG prime, output is some 4D theory, which you have some understanding. And the way to construct this Calabi-Yau sweeper is rather kind of concrete. So depending on your AD type, you have this kind of well-known singularity classification. So you just use this FG and FG prime. So it's 4 variables, 1 equation. So it's going to cut out a street. So Calabi-Yau street. Calabi-Yau street for singularity. So using this X, you obtain 4D theory. So for instance, if you think of AN theory, AN is described in this manner. AN is described in this manner. You just obtain this Calabi-Yau street. And the slogan for this thing is that in order to define this 4D theory, the input data you use is this Calabi-Yau sweeper, basically nothing else. So in a sense, the slogan is that whatever this 4D theory is, you can understand this purely in terms of Calabi-Yau sweeper. At least as a slogan, I think this is something to say. And sorry,
just on the Zoom.
Oh.
Yeah, so that you can. Thank you.
Right. And I just want to say that the relation, because this is Higgs funder conference, and I just want to get to somewhere Higgs funders. I want to relate this to what is called class S theory. I think people in Higgs funder may have seen something about class S, and the thing to kind of remember is that in terms of again input data, you just use the Lie algebra G and comparing a surface and some decoration, which corresponds to meromorphic Higgs funders or something. So that's what class S theory is about. And the claim is that in the previous slide, I just talked about this like GG prime theory. When G is type A, AK, then they have a intersection. So any AK G prime theories are known to be class S theories. And you can be explicit, like your Riemann surface is like CP1, and then your marked point information can be specified. So the only thing I want to convey from this slide is just that class S and this GG prime theory has a non-trivial intersection. this doesn't mean to say thinking about, the scale doesn't matter. It's like only the topology matters. I don't mean to say that like a GG prime theory is as large as class S, or that's not the point. It's just they have intersection, but they are different classes. So I'm going to talk about basically something about the GG prime theory. So in the case where it has intersection to class S, I do expect to see something about different complex structure of the Higgs modulus space. That's kind of where I.
How do you understand the complex structure of the Riemann surface in GG prime theory?
So, so the mathematical thing I can say is that I think I'm actually going to say more later in the next slides. Right. And there's this notion of BPS quiver, which again, kind of for mathematicians, it is just a quiver that's assigned by, whenever you think of the theory, when you make some choice or the vacuum, then you obtain a quiver. And so this part I'm going to explain more from the algebra side. But since we predicted that this quiver is kind of particular form, and particular form is the following. If you think of A2, you just take a product, just naive product, but then you have this kind of diagonal arrow. So additional information you think of in addition to just thinking of the product of quiver, this diagonal arrow. So if you think about this A2 is kind of the local picture, and the rule is local. So if you understand this A2 case, that's kind of that's about it. And then you have additional information about this kind of potential. And this part I'm going to explain more in the algebra section. But kind of one of the main questions I want to ask is that I want to understand this quiver in terms of geometry. That's one goal of the talk. And I think this slide is supposed to answer like Hirokyo's question, which is that. So okay, this slide is also like not. I don't expect this to be comprehensible to everyone, but I can say a few words. So this class S theory, I'm actually thinking of what is called the holomorphic particle twist. So that the C direction is topological. And then this kind of string theory way of understanding this class S in terms of this X, as I explained, the dependence on X is also topological, in the sense that it is like A model direction. So I have some mathematical work on making sense of this. There's a framework for the twisted string theory developed mathematically by like Costello and me, and also like I did some work with Surya Raghavandran. But that's not quite the main point of the talk, so let me not say much more about this. The only thing I want to say is that, as a mathematician who wants to understand what's going on in this kind of the class S theory, like really mathematically, certain things for the twist is necessary, which is a process of making things much easier and accessible and mathematical, and with which things can be understood in terms of this X. Again, simplified version, which is that this square category of X. So whatever you want to understand this twist of class S theory, I can try to understand purely in terms of Fukaya category of X, if I find some Calabi-Yau. So the difference from the previous slide slogan was that the previous slogan was the really physics slogan. For the theory proper, what's called the physical theory. Information of that is included by Calabi-Yau. But now, after deciding to lose a lot of information, that's kind of what I'm calling by this HT. Then much of information, which is sort of what is relevant for a lot of mathematical objects, that can be encoded purely by just very rough invariant of Calabi-Yau, namely Fukaya category. You just kind of don't remember everything about kind of the Calabi-Yau. You only remember Fukaya category, but that's enough to understand the certain subsector of for the group 2 theory, and it can be made as a mathematical plane. Okay, so so I can say physics result. The result is that, so previously I worked with this AD kind of the quiver. Now the claim is that I can work with trees. For each trees, I can construct certain Calabi-Yau triple. And whatever this BPS quiver can also be understood as a generalization of a CMV set. And then somehow I find relation to Fukai category in a sort of the precise manner. This is the physics result, and the somehow mathematical result is going to be sort of the can be said better in the other sections. And the another working progress is that this construction can be generalized to, I think, thickened trees. So tree, but like each arrow can be like thickened. You can have like n parallel arrows. In this case, it's quite general to the extent that you know, I think it's like much more general theory. It, I think, includes what is called the pure SU2, and yeah. So the claim is that it seems like I can produce some physical theories much more general than this GG prime theory, and has like a lot more intersection with PSS theory. I don't really know kind of the how exactly in terms of like scale and how to draw this, but it's certainly kind of a lot larger class. Okay, I think this is it for the physics part. So that was the first iteration of the story. Now I think it's going to be algebra. It's referred to Quivers and so on. So I'm starting with some kind of the abstract looking definition, but I'm going to make it kind of the concrete in terms of examples. So we start with the sort of the DG algebra or DG category, and then there's a construction called the n Calabi-Yau completion, just making it as a n Calabi-Yau algebra. But I think it's just better to understand this in terms of examples. So whenever you have an algebra, you can sort of try to do this procedure of obtaining Calabi-Yau completion. And here are important examples. So first of all, when you have a quiver, you think of path algebra. And this pi2 of path algebra just refers to pre-projective algebra. This is essentially just about like taking cotangent bundle of your quiver. So in the Nakajima-Gilroy construction, you think of the sort of the other way around. The arrow the other way around, doubling. It just exactly corresponds to that. So that this becomes cotangent. In other words, like two-dimensional Calabi-Yau. So that's one example. Another example is that if you start with a d-dimensional variety, let's say like smooth projective variety, and if you think of d plus one dimensional Calabi-Yau completion, so this is exactly what you want to do, which is that you just think of the canonical d plus one dimensional Calabi-Yau manifold you would assign. You can come up with given d-dimensional variety. We just take the total space of canonical bundle of your d-dimensional manifold. And this algebraic procedure, whatever that is, that does give such a thing. We just give category of coherent sheaves on this total space of canonical bundle. Another example from, let's say, the symplectic side is that if you have a nice function for the left set vibration, then there is something called the Fukai-sided category. So like vanishing cycles, thinkers, and so on. If you have such a d-dimensional object or category, one way to obtain d plus one dimensional category out of that is think of d plus one dimensional fiber. But to get that, you don't just take the any random fiber of f that would be d minus one dimensional. you need to add two-dimensional and with coordinate u and v, and then take the fiber, generic fiber. That would be d plus one dimensional, and that's kind of the modeling. And the d plus one Calabi-Yau completion is essentially kind of high category of such a fiber. So as you can see, Quivers algebra somehow by definition is like one-dimensional object. So it's one-dimensional to two-dimensional, d-dimensional to d plus one-dimensional, d-dimensional to d plus one-dimensional. So you have this idea of Calabi-Yau completion, and this is geometric examples or algebraic examples in the case of Quivers. So one thing you may want to do is for several purposes, Calabi-Yau is known to be highly important. So let's just decide that we want to understand some Calabi-Yau or Calabi-Yau algebra or Calabi-Yau category using this procedure. But because note that the construction works for any algebra in pi n, it is just that in these examples, it's the right-hand side has nice description because the dimension is like one higher. If your dimension jumps like a 2 or higher, or like a lower, you don't necessarily have a nice canonical geometric description. You don't expect that. That's kind of the upside of this construction. So given that, if you want to get 3 Calabi-Yau, then expectation is that you somehow want to start with some two-dimensional object and then do Calabi-Yau completion to get to 3. And given that we like Quivers, and Quivers are one-dimensional, one way to obtain two-dimensional object, two-dimensional algebra is just take tensor product of these Quivers path algebras. So you just take tensor product, and this is going to be two-dimensional, and also chronological sense. And for each vertex, I'm going to be having the product vertex. And then, for each arrow of Q and for each arrow of Q prime, I'm going to be having horizontal and vertical arrows. And then, of course, I'm expecting to, I do have these courtesy scale relations for every pair. So I think it's good to have some example. So if you think of A3 Quiver here, in the horizontal, and A2 Quiver, the vertical, if you take the tensor product of tensor algebra, you get this Quiver. And then, of course, the squares, they are commuting. And then the next question we are getting at is, what is this kind of the Calabi-Yau completion of this thing? So this is kind of the well known. I think this part, this as well as other things are worked out by Keller. I think this part is like not that difficult. This Calabi-Yau completion can be described in terms of what is called the Ginsburg algebra of Quiver with potential. And that's how you see the Quiver with potential that I introduced in the previous section earlier. Which is that, you just think of this like A2 path algebra tensor product. But then you have this relation, this B prime A this way and A prime B this way, they do coincide. And if you do Calabi-Yau completion, that is, you just add an arrow here, and then add what is called the potential. But then the way the potential works, it is through taking this derivative. And by taking derivative, you obtain the original relation. So in other words, the 3 Calabi-Yau completion is just by adding an arrow and the potential. You just remember what was happening in this original tensor product of the path algebras. So this is just a construction. In other words, it's you just kind of think of the path algebra and then do this kind of canonical procedure, and this is kind of completely under control. And then the next question is, can you understand what's happening in terms of geometry? So let me try to give you examples from algebraic geometry. There are a lot of words, but somehow not much is happening. I think it's also good to just see examples. So if you have A1, algebraic geometry, you have an A1, the affine line. That is described by this, what is called the Jordan quiver. One vertex, one set group. And then like representation theory of that is exactly about, representation theory of this KX. And then another like one-dimensional object which does admit this quiver description is this famous work of Bellinson. You have this what is called chronicle quiver. So the claim I'm making here is that let's say derived category coherent shapes on P1 is equivalent to derived category representations of this particular quiver. So study of P1, at least in a homological level, is in a way equivalent to a study of representation of such quivers. So these are two one-dimensional ingredients. And using that, and using the process I just described of, I just described a local picture of take the path algebra tensor product and then add an arrow. If you follow the procedure, then you get a quiver into potential. And then that's exactly kind of describing what you want it to have, which is kind of Calabi-Yau completion of this product space. So options for farming is that one way to obtain two-dimensional algebra is thinking of two one-dimensional algebra, namely path algebras of quiver, take tensor product, and three Calabi-Yau completion. In some cases, like these quivers, I can understand that from algebraic geometry. I have these algebraic geometric models for those. But there's kind of, one can say there is a limitation to this method, just because like algebraic geometry is pretty like rigid. At the end of the day, actually, like I explained in this manner, but you could have just started with this such a surface and then describe the corresponding quiver. And this is sort of not too difficult to describe in this manner. But there are only like so many kind of surfaces which admit a quiver description. So if our goal is to understand like really large class of quiver and geometry for that, the algebraic geometry is kind of limited. So that's one way to see read of our result, which is that we describe basically any describe the tensor product type quiver in terms of square category. So we just give a geometric model for this Calabi-Yau completion in this general. Yeah, that's what I said here. And again, kind of I think the more interesting bit is that at the moment, I think we have a proof for trees, but I think for this kind of the thickened tree, I think I do believe that the theorem is going to work. I just don't know how to exactly kind of state the theorem. Anyway, so we can kind of find a geometric model for very much larger class of theories. So I think this is it for the second talk. Any questions for the second talk?
So what is the relation between this y and the previous x in this simple?
Great. So I think that was actually kind of I didn't even like read. So one was like resolution, and when comparable. So I think kind of in this, in this equation, I think y is just maybe like you have 1 instead of 0 there. Just resolution. But the point is that it's going to be much more general in general.
But you also stated that this Fukaya category, category, algebraic category, realize the Fukaya category of Y. But on the other hand, you also said that this is what X, the derived category coherency from X is. So,
Okay, no, sorry.
Why is it similar?
So this slide can just be ignored for the purpose of this talk. That's not the point of my talk. Derived category coherency does not play any role. So for certain quivers like these, it happens to be that like they also admit realization from algebraic geometry, but basically only for these exemplars, because these are coming from A1, P1, and only for A1 and P1, those are the one-dimensional kind of the thing you can construct, out of which you can construct quivers. For any general other class of quivers, like a pair of quivers, simplex geometry is like much more like flexible. So that's what I'm going to talk about in the next talk. Any other questions for this talk? Okay. So final talk is about geometry. I somehow think that this part is maybe most successful to the audience in this conference. This slide is like a little more like maybe abstract, but like from the next slide, I'm going to work out examples so that you can see what I mean. So I want to start with a definition of left-side vibration. Let's say, for simplicity, from n-dimensional complex manifold to C, and it has finitely many critical points. But the important thing is that it is basically kind of looks like a Morse function. So for each like near singularity, it just looks like this sum of squares. And then if you think about for a regular value, the inverse image of that regular value is going to be smooth 2n minus 2 dimensional manifold. And the important information that you try to record whenever you have such a thing is you just have these kind of critical values. You pick this like a random regular value, which is not one of those kind of critical values. You think of this path, but then you see some what is called vanishing cycles. And those are the information that you want to keep track of. Because there is some abstract theorem saying that this information of left edge vibration can be encoded in terms of the generic fiber F together with such vanishing cycles. In other words, if you have such information, you can construct left edge vibration back. You can recover it. So it's a very abstract. So let me work out the easiest example. I think if nothing else, you can understand this one in addition to my movie recommendations. So left edge vibration, the easiest case is this kind of Morse function. Fxy equals x squared plus y squared. And I just want to understand this in terms of fibers and vanishing cycles. So just to be concrete, let's just set u to be x plus iy, v to be x minus iy. Then f looks like uv. And then you just think of fibers over 0 over non-zero. If you think of over 0, of course this is uv equals 0. Fiber over t, non-zero value, is exactly c star, which is in this case, like for the Weinstein manifold, it's actually equivalent to, you should think of this as a cotangent mode of S1. So this is kind of what I draw there. You have T star S1 as a generic fiber. So this is S1, and this is my picture for cotangent bundle of S1. And then UV equals 0 just looks like this cone. So that's a picture for regular fiber and singular fiber. But important information is that there is, and just from the picture, like you can see that there is a vanishing cycle. As you move this T to 0, as it kind of gets to 0, this vanishing cycle is becoming vanishing, like literally. So that is kind of worked out for this particular T. Vt it can be parameterized by this, and there is a circle, and that circle is exactly shrinking to this point. And the claim is that this information of f can be recovered, or I didn't explain, can be recovered entirely from this information of regular fiber and vanishing cycles. So one more example. I think of the A2 local model. And if you remember, A2 was x cubed plus y squared. But you do what is called the morphification. That is to say that you just kind of make it, at least locally, looks like Morse function. And this is one way to do it. Because then some of the numbers are kind of easy to read off. This is kind of typical multiplication, so that if you take derivative with respect to x, you get 3x squared minus 3. So, x is like plus minus 1. That's kind of the critical points. And the image of that is going to be critical values, which is 2n minus 2. So this is kind of what I draw. This f, the base of f, the values of this f. So 2n minus 2, those are the special points. You pick a generic point 0, and you just kind of think of this vanishing path. And you also think of regular fiber as it looks like this, because 0 is the regular value that I chose. You get this regular fiber. But to describe this better, you think of the projection to just C, projection to X. And then you can easily see that it's a breast cover, breast that is like minus square root of 3, 0, and square root of 3. And then you can easily see that this F is one's punctual torus, right? This simplification will be torus. So from this, you get torus. And what is happening here is that I think this is probably kind of familiar to Higgs bundle kind of people, because it's actually usual double cover of the special curve construction. So this is pictured in, let's say, the UV curve of C, and you think of the double cover, and this is becoming a circle, right? So that circle is living inside of this F, generic fiber, right? Doubling of this thing. Doubling of this thing is another circle, and that's drawn in this kind of the one's punctual torus, like this. And the vanishing circles can also be drawn in a concrete manner, like this. And again, the claim is that just by understanding this regular fiber, together with the vanishing cycles, and the sort of information between them, like intersections and so on, that determines the left-edge vibration. So the thing I want to do is, if you remember a bit from the previous talks, I want to start with a kind of quiver, and then I want to find a geometric model for that. And the geometric model, is going to be involved left-edge vibration. But in order to construct left-edge vibration, I want to construct kind of regular fiber together with vanishing cycle information. That's what I want to do. And so this is kind of exactly sort of the hint for what I need to do. I want to construct such a thing. Basically, kind of the given A2 quiver, I just want to understand how construction which gives such a one's punctual torus. So that construction is known to be a plumbing. I'm not going to spend like too much time, but think of this A2 quiver case, which was kind of mentioned in the previous slide. There are two basically kind of strips, pistal S1, and they are glued together to give punctual torus that was discussed in the previous slide. And there's a geometric construction in terms of gluing. And that is given by gluing this unit, this bundle of sphere. In our case, we are taking n to be 1 in a particular manner. Somehow, zero section of one thing is glued to the cotangent fiber of the other thing. And the claim is that for any quiver, for each vertex, you obtain this unit disk bundle, and then this kind of you can perform plumbing, meaning gluing for each edge. And then you obtain this plumbing space that's going to be what we are going to take to be the generic fiber. But because each vertex also has sphere in it, so like T star Sn, or in our case T star S1, you can also take this S1 to be the vanishing cycles. And what I told you is that the information of this generic fiber together with these vanishing cycles, that does determine the left edge vibration. And then, of course, this claim is that if you started with AD quiver, then this process does give particular left edge vibration, and that actually does recover the singularity associated to gamma, right? Like x to the n plus like y squared and so on. In the case of type A-1. So then I can now state the main theorem. The claim is that this quiver that I obtain, there is a particular types of representations you can consider, which begins for algebra and BG modulus. It's essentially something like a modulus over the Jacobian algebra, the right version thereof. That is described in terms of some Fukaya category, but this when just means that it's a subcategory generated by the vanishing cycles, namely the spheres that's coming out of the construction before. So a few things one can say. Vertex, so each information on the left-hand side does have geometric distribution on the right-hand side. So vertex here of this kind of tensor product of quiver correspond to Lagrangian free sphere. Oh, sorry, I should have said. I do consider this Thom-Sebastian sum, which is that ft was a function from C2 to C, ft prime was a function from C2 to C, and you just can't add them up. Like you have like a xy variable, zw variable, you just add them up, and now it's a function of 4 variables, that naive construction. In which case, the vanishing cycle is known to be given by join of vanishing cycles. So circle join circle is 3 sphere. It's like Lagrangian 3 spheres of the Fukaya category. Those are the vertices, and edges keep track of the intersection of these Lagrangian 3 spheres, and then the potential that you obtain here is about like Bloomfield discount, and you can see that doesn't really see the higher model. And the part that we've been working on to make this theorem stronger is, I said earlier that the construction seems to be working for a thickened tree, but it is technically a little bit harder because left edge vibration, the example I considered was from C2 to C, but now the domain is not going to be C2 anymore. I think the same construct seems to be working, but there are some technical difficulties, so we are working on that. Okay, so as a summary, for the physics part, this Tensor-Product BPS quiver was described in the study kind of further for like many other properties for these kind of pairs of ADE. Now it seems like it can be, you can put thickened tree for each pair, so that in particular it includes like pure SU2 and so on. The second, the Calabi-Yau completion, it is kind of the algebraic construction, and because we are working with more flexible symplectic geometry world, I found some kind of geometric model for such a algebraic thing. And third, to understand this kind of what's happening in the geometry, we think of the Thom-Sebastian sum of the left edge vibration, and then thinking of the vanishing cycles is very hard. That's exactly the underlying geometry for such a construction. And I think the one-line summary is that this tensor-product BPS quiver, Calabi-Yau completion, and Ham-Sebastian fibers like category, they seem to be all kind of the same thing, and that's how I was kind of giving this talk from 3 different perspectives. Okay, thank you.
Are there any questions or comments?
So I assume that this construction is unique, like the completion is unique. Is it?
You mean the algebraic completion?
Yeah.
Right. It is unique, and I think what is actually hard from simplistic side is that there are like just so many choices, and one can show that things are like up to some like Einstein equivalence. Like there are a lot of kind of equivalences, and yeah, that's one thing I mean by kind of we need to find the right statement to state. So this is like rough statement. It's a little hard to say kind of what exactly is the equivalence class to say the precise form of the statement. The content is there. You just need to figure out how to say it.
Any other questions?
Is there any part of this that would go beyond quivers that happen to come to you as tensor products?
So this construction is really about tensor product. Each quiver can be quite general because it's a thickened tree. So each tree can be non-trivial quiver, right? Like PRC2 is already just one part of the. Just by taking one of them to be A1, this is already something. But other than that, certainly this way of thinking doesn't work. Oh, so cubic potential just means in terms of potential just means kind of cyclic words in kind of path algebra, and cubic means that you just have 3 terms. So yeah, these 3 terms like this. In this is x, y, z. In this is like interesting. So anything is coming from the kind of anything that's coming out of this construction is only having cubic terms, and having cubic terms corresponds to having product. So if you have a quartic term, that would mean that you have like higher product M3. So n plus 1's power means that you have n higher product.
Any other questions? So in the socialism, you said that cubic term and higher mass product partitions. Is there any reason?
So I think it's like essentially because this plumbing space is kind of simple. Some of the way it was constructed is simple, and it just kind of goes through even after taking the product or test product. Essentially, that's good.
Any other question?